All right, so I wanted to finish up and talk about pyramids and cones. And the good news is the thought process for finding the surface area of pyramids and cones is pretty much the same. It's just because of the nature of the shape, we're going to have to do things a little bit differently. So anyway, some vocabulary for you. The vertex of a pyramid, which is the same as the vertex of a cone, is simply the common vertex of the lateral faces, or it's where the triangles meet, or it's this top point here. The same thing for a cone. At the same time, there's a slant height that we have to consider. Okay? And the reason why we're talking about a slant height, and I'll do this pretty quickly, is find the surface area. Again, we can do this in pieces, where I can find the area of this base, how much paper is it going to cover, how much is it going to take to cover that, and then find the area of these triangles. How much paper will it take to cover those? And to find the area of this triangle, we have to do 1/2 base times height. And the height of the triangle would be that guy right there. But that triangle is slanted in. All these triangles slant in to find to meet at that vertex. So that's why we're considering a slant height. This is our slant height that we call L. Very often we let it be L. And it's the height of that triangle. Okay? And so it's represented by that. That's the slant height. Now, that's different than the actual height of the pyramid. Remember, the height of the pyramid needs to be that perpendicular height. So this segment right here is the height of the pyramid. If you draw the slant height and the height of the pyramid in, and then you can connect it right here, and you get a right triangle. So we can use that to our advantage. If we ever need to find the slant height, then we can kind of do that by using right triangle stuff. Okay? So, for example, example number 1, they wanted to find the area of the lateral face of this pyramid. So the area of the lateral face, the area of a lateral face, would be something like this guy right here. We want to find the area of that, which is just a triangle. Okay? So to find the area of that lateral face, right, it's a triangle, we're going to do 1/2 base times height. Well, the base is 16. It's just going to be the same. This is a regular square pyramid, so those bases are the same. So this is going to be 1/2 times 16. And then we got to find the height of that triangle. The height of that triangle is the slant height. It's actually L. So we got to find L. Okay? Well, we know that when we draw the height of the pyramid in, then we get this right triangle, and that right triangle has been pulled out down here. Now, the height of that triangle is the height of the pyramid, which is 15. This down here is going to be 8. It's half the length of the base to get from here to here. Okay? That makes any sense. So from here to here is going to be half of 16, because we're right in the middle of the square right now, and we get out to the side, it's going to be half, that's going to be 8. So now we can do Pythagorean theorem to find that slant height. The slant height is the hypotenuse. So we get 15 squared plus 8 squared. Right, so this is going to be 225 plus 64. So L squared is going to be equal to 289. And then we square root. You can't see that over there, but so L is going to be 17. So now we know the slant height is 17. Okay? And then we go find that. So half of 16 is 8. 8 times 17 is going to be 136 square centimeters. So each of those triangles are going to be 136 square centimeters in area. Okay? So how do we piece this together to find the surface area of an entire pyramid? Well, it's the same thought process as it was for the prisms and the cylinders, right? If I want to find the surface area, then think about how we're going to do this. I'm going to cover the base in paper first. So I'm just going to write big B to cover the base with paper first. And then I'm going to add to it the sides, the lateral area. Remember, this is going to be called the lateral area because it's the area of the sides. Well, think about how we're going to do that. Right, I'm going to find the area of each triangle and add them up, right? So that one, that one, that one. Well, each of those triangles uses a side of the base to find the area. And then we're going to add all those up. Well, if I add up all the sides of the base, then that's the same thing as finding the perimeter. Okay? So we're going to throw a big P in there for the perimeter of the base. But it goes into the area formula of a triangle. And so the lateral area ends up being 1/2 times the perimeter of the base times the slant height, because again, the lateral faces are triangles, and we have to have the height of the triangle. That's a little bit about why we're doing what we're doing. If that doesn't make a ton of sense, come in and see me, and I'll try to explain it a little bit better than that. But this is your surface area formula. Bottom line is find the area of the base, find the perimeter of the base, and make sure that you can find the slant height of the pyramid, which is the height of one of those triangles, triangle sides. Okay? So for this one, how do you find the area of the base? Well, it's a regular hexagon. So we got to do 1/2 ASN, then find the perimeter of that base, which is just add up all the sides, and all the sides are 10. So we got 10, there's going to be 6 of those sides, so we can do 10 times 6 to find the perimeter. And then multiply that by the slant height, which is 14. Okay? And then you just plug in what you know and go to work. The apothem for that hexagon is 5 times radical 3. The side length is 10. There's 6 sides. And now we're off and running and just simplifying. 10 times 6 is 60 times 14, right? So we got 1/2 times, again, 10 times 6 is 60 times 5 radical 3 plus half of 60 is 30 times 14. Half of 60 is 30 times 5 radical 3 plus 30 times 14 is what, 420. 30 times 5 is 150 times radical 3 plus 420. Okay. All right. So we continue here. So 150 times the square root of 3 plus 420, and that gets you about 679.8 feet squared. Okay? So find the area of the base, find the perimeter of the base, and shove it into that formula, and you're going to be in good shape for a pyramid. Okay? Now, how does this thought process translate to a cone? Well, here's a standardized test practice problem here. Let's find the surface area of this cone. Well, it's kind of the same thing. The surface area is find the area of the base plus find the lateral area. I'm just going to put lateral area LA. Okay? Lateral area being this side stuff right here. Well, what shape is the base in? In a cone, the base is a circle. So the area of the circle is just pi r squared plus. Now this is where it kind of gets weird. And I'll tell you a little bit about where it comes from, right? To find the lateral area, we have to go around the cone to cover it in paper and then multiply down this way to get to that vertex. Well, around the cone would be 2 pi r for circumference, and multiplying down this to the vertex would be the slant height L. Well, we're not going straight down, so 2 pi r would be all the way around but when we get down here, it's not quite 2 pi r anymore. So we have to lose some of that area. And that's just my cheap way of letting you know that the lateral area formula is actually, the lateral area is going to come from pi RL. We dropped the 2. We're going to lose some area because we're dropping to a point in a cone versus in a cylinder where it doesn't come to a point. So we dropped the 2 from the circumference 2 pi r. Okay? Anyway, again, if that doesn't make a lot of sense, you can come in and see me. I'll try to explain it a little bit better. Bottom line is the surface area for a cone turns into pi r squared plus pi RL. Right? So r is 6. And the slant height here is something that actually we end up having to find, right? We don't have the slant height. This is the slant height. What we have is the height of the cone. But we can use the height of the cone and the radius and the fact that they're going to form a right triangle with the slant height to go find that slant height. So this is 8, this is 6. To find the slant height, we just use Pythagorean theorem. L squared is equal to 8 squared plus 6 squared. L squared is equal to 64 plus 36. L squared equals 100, square root, and L is 10. So now the slant height is 10. And we're ready to keep chugging along here. So 36 pi plus 60 pi going to get you 96 pi. And that's actually answer B. Okay? So surface area for a cone, pi r squared plus pi RL. All right? Got one more here, and we're going to make a traffic cone, right? And to make a traffic cone, we have to pour some melted plastic into a mold, right? Now I want to know how much orange plastic I'm going to need to form just that part of the traffic cone, the orange part of the traffic cone. So what I need is the lateral area. This is the lateral area of that cone. Okay, and there's some approximations here. The radius is 5.7 inches, and the height of the cone is 18 inches. So find the approximate lateral area. Well, in our surface area formula, pi r squared is the area of the base. Pi RL is what we use to find the lateral area of the side. So really all I need is this. So the lateral area is pi RL. No problem. The radius we know is 5.7 inches. The slant height, L, we don't know. Okay? But again, if we were to represent, there's the height of the cone, there's the radius, this is the slant height. It's a right triangle. We can use Pythagorean theorem all over again to help us find the lateral area. Now we've got to do L squared equals 18 squared plus 5.7 squared. So 18 squared being 324, 5.7 squared being 32.49, and then we're going to add those in square root, and we get 18.9. So the slant height, so L ends up being 18.9. Okay? So 18.9 times 5.7 gets us 107.6 pi. And we can multiply that out if you'd like to get an approximate lateral area of 338.1 inches squared. That's just for the orange lateral area. Okay? All right, hopefully that makes enough sense. You got your surface area formula. Let's give your homework a try. It's out there in Canvas.